Okay, so this is day one of 2 days of work on applications with logarithms. And there's sort of two main types of questions that we're going to look at, and then each one kind of has some subtypes. Okay, so these equations that we're looking at here, these are for the exponential equations. These to me are really the interesting ones because there are so many real life applications of exponential functions. And not only are they like real life ones, but they're like real life ones. Like people use them all the time and they impact our day-to-day lives, and they're part of the, sometimes people can't see why are we learning this. They can't see the value of learning something, whereas with this you really can. This is believable that you could understand that people use these equations in their day-to-day lives all the time. At the bank, scientists, like all kinds of things, okay? And then the second kind is like the logarithm scale questions, and we'll do a couple of them today, and we'll talk more about the logarithmic scale in detail tomorrow, I think, if we get time. And they're relevant, but they're so simple that they're just not as interesting. In grade 11, you would have done exponential applications like this, but you couldn't solve for time unless it was a special case. So again, they're not as interesting. Now that we have the power of logarithms, we can solve for more things, and we can see how, like I say, how useful to real life these applications are going to be. Okay, so that's the intro. Let's get into it. When you've identified a question as being one of the exponential type, you are going to be using one of those three equations. Okay? So you need to know the equations, and you need to know what each part means. What's the A, what's the R, what's the T, what's the N, all of those things, okay? And obviously that's in the list in your handout in front of you. Growth, you're adding. Decay, you're subtracting. And you use this one when you're given the multiplier, so there's some special cases where you use that one. It's not 1 plus or 1 minus. You just have the value that goes in the brackets. The rest of the equation is the same for both of them. Okay? We don't always use A. You could. We usually pick a variable that makes sense for the question. Okay? But let's say you use A. The A on the left side is the final amount, and it's really important that you get these in the right direction, otherwise your answer is going to be really strangely wrong. And the A with the little subscript 0 is the original amount, the starting amount, and it's a 0 because it's like at t equals 0, at time equals 0. It's sometimes called A naught. That's a mathematical term. I think it must come from like be British. But it means 0, so A naught. And if it's growing, then A will be bigger than A naught. And if it's shrinking, then A will be smaller than A naught, right? So again, if you get those flipped, your answers might end up being really, really strange. R is the rate of growth or decay. So if you're given a rate, then you're going to be using one of those two, depending on whether it's growth or decay. T is the length of time that has passed or that is passing. N is a bit of a tricky one, although you've seen it before. It's the length of time until one period of growth or decay occurs. Okay? And we'll see an example of that when we get there. And then, as I said, B, you use this equation, which has the B in it, if you are given the base directly. And the question would say something like doubles, triples, like a population of rabbits is doubling or tripling, or the half-life questions, you can go straight to using this. You don't need to do the 1 plus and 1 minus versions. Yes?
So if it like doubles, triples, or half-life, is the B going to be like 2, 3.5?
Yes, exactly. Okay, so we're going to identify the type of question that it is, identify whether it's growth or decay, whether it's exponential or logarithmic. There's a lot of like making sure you're kind of taking the right approach, and then we'll talk about how we actually go ahead and solve these. So first one, if the population of a city is 178,500 in 1990 and is growing at a rate of 2.1% per annum, in how many years will the population be 210,000? So in how many years it's asking us to solve for time. And then there's a second question, which we'll get to obviously afterwards. When will this occur? So this is an exponential type question. The first two that we're going to do are both going to be exponential. The second two will be the log scale type. First thing you're going to identify, it's not usually hard. It should be clearly somewhere in the language, but once in a while it might be a bit tricky. And you certainly don't have to write this down, but I'm going to, just to show my thinking, is this a growth or decay question? And this one is growth. And we know that because it uses the word growing in it, but it might say increasing, decreasing. You have to know that half-life is a decreasing and know that what the multiplier is for half-life. So some of these things you do have to kind of just know, all right? Once I realize that it's growth and we're given the percentage, it's not the one where we're using B, I'm going to write out the equation that I'm going to use. P, so I'm using P for population instead of A, right? Equals P naught 1 plus R to the T over N. And then I think a really good strategy is to list our givens. So now that we know which formula we're using, I'm going to come over here and I'm going to write each of those things out. P equals, P naught equals, R equals, T equals, I don't know why I'm writing them so small, N equals. Whoa, that's too big. And then we're going to start filling them in with the information that we're given. So what's P? Maddie? 210,000. That's the final amount. It's growing, so it's the bigger number, right? Good. What's P naught? You don't have to do them in the order, but I think you're probably going to be able to do that this way. This is the 178,500. What's R? William? 2.1%. And again, you certainly don't have to write all this out, but we have to convert that to a decimal. So how do we do that? 2.1 divided by 100. And if you need to use your calculator for that, then go ahead. 2.1 divided by 100 as a decimal, 0.021. You can go straight to that. You can just write 0.021. You're just moving the decimal place, but sometimes people do make mistakes when they just move the decimal place, so make sure you get that right. What's T? What we're trying to find. So I'm going to put a question mark. And what's N? Anybody know, Evan? It's 1. If it's not 1, then it's going to be a bit more obvious. If there's no number, then it's just 1. It says per annum, per year. Annum is a Latin term for year. And so it means once a year, not every 3 years or every 5 years or 10 times a year or something like that. If it was one of those things, then you would have to consider what N is. But it just says per year, each year, once a year, so N is 1. Okay? Now, I've got this in the way. So we're going to fill this in. Now, I'm going to fill it in a bit of a weird way, but I'm going to tell you about why once we get there. And then the next example, we'll see how we really kind of show our steps. So I get the equation of P equals 178,500 to the 1 times 1.021 to the T. T over 1 is just T. Now, why didn't I sub in for P? Just because I wanted to have this brief conversation about this. This is the equation that represents this relationship, this situation. And you could have a question, and this might have been the kind of stuff you did in grade 11, where you create this equation, sub in for T, and solve for P. They said, what would the population be after 10 years, after 20 years, after 30 years, right? That would probably be the other way you would use this equation. So P and T are kind of your unknowns. You could have anything be the unknown, but that would be sort of the standard. But now in grade 12, now that we know logarithms, we can sub in for P and solve for t, which is the majority of what we're going to do. There may be a couple of questions in the practice. I don't think there are in today's, but somewhere where it tells you what t is and you solve for p, and then part b is it tells you what p is and you solve for t, you know what I mean? So I just wanted to briefly kind of point that out, that it is possible to solve for other things other than time. All right, now let's actually do this. 210,000. So you don't have to show all those steps. You can skip straight to that. In terms of like strategies or, being careful, I think writing that out and getting those right on the side is a good way of slowing your thinking down and just organizing your thinking and make sure you're getting everything into the right place. This is the same as you might see in physics. They often talk about listing your givens. Same idea. Some questions might be worded a bit awkwardly, or they might be asking something in a bit of a different way. And so again, listing those things out can help with that. Those would be my recommendations, but write that and then you can just sub everything in and go straight to that. Now what do? Now we have to solve for t.
You just put it through the log.
Not quite yet. Well, you could take the log of both sides, but we're going to do something else first. Evan?
Did we rearrange it?
How would we start doing that?
Bring it all to the right side.
What would I do first? Anybody? Maddie?
Divided by that.
Divide both sides by this. Yep, thank you. Now that we've got it set up, after identifying the type and everything, the steps are all basically identical from here moving forward. Okay, we divide both sides by p naught. You always divide by that to start. I suppose you don't have to, but you can simplify this. If it's going to simplify, it's going to be less writing because we're going to write it a few times. Turns out this one simplifies in kind of a surprising manner. It's 20 over 17. It's a little, strange. It doesn't look like it should simplify to that, but it does. So we've got 20 over 17 equals 1.021 to the t. Now what do? Anybody? Yes?
Take the log of both sides.
Yeah, we can take the log of both sides or rearrange. I'm going to do the rearranging one. So the rearranging is the base stays the same. 20. I'm doing this backwards. Log base stays the same, and then 20 over 17, and that equals t because logs find exponents, but I always write it the other way because then it's t equals log base 1.021 of 20 over 17. Okay, if you're using the change of base formula, then you're writing this out next, or you're just putting it into your calculator. I don't care which one you do, obviously. But one way or another, you're putting this into your calculator. And yes, I would recommend you try it with me to make sure that you are getting the right answers. We're working in years here. Yep.
When we're rounding, how many decimal places should we have?
So the questions on the test will probably say what to round to. If it doesn't, and you're writing a test and you're nervous, you can always ask. But just pick something reasonable. Don't round to 5 decimal places. Don't round to the nearest 10. Like 10 years. I rounded up to 10, right? Don't do something weird. Keep a decimal place kind of thing. Any other questions? Yep.
Why wouldn't we do round with 8? Because normal? Because it's like, it asks how many years, but like, you can't.
Well, 7.8 years is reasonable. That's fine. I understand what you're saying. We're actually going to explore that a little bit more tomorrow with a better example of exactly what you're talking about. But for something like this, I think having 0.8 of a year, like a year is a long time.
Yeah.
7 years or 8 years, like if you were at 7.4 and you round it down, you're rounding half a year off. And if you sub that back in, you wouldn't get close to that, right? So I think it makes sense to keep a decimal place or two in this case. Also, the second part of this question, we're going to need that decimal place. When will this occur? So the expectation when you're solving that, when you're doing that part of one of these questions is that you determine the year and the month within the year that it occurs. So what year does this occur? 1997, right? Because it's 7 years and some after 1990.
Yeah, I was just gonna say, if it's, what if it be 1997.8, so we're looking at.
Hold on. I'm going to write this down first. This will occur in blank month of 1997. How do we find that month? Mara, what do you think? Oh, you're not sure. You were going to say.
Would you not go from the 8th month?
8th month because it's 0.8. But that's 8 out of 10 because this is a decimal system. It's base 10. So if it was 8 out of 12, then yes.
You multiply 12 by 0.8 to find 80% of the year, and you get,
Okay, hold on. So what I'm actually going to do is I'm going to subtract 7. So I keep all the decimal places, but you're right, 0.8 is going to get you close enough. But this is going to be a bit more exact. And then I want 0.8 times 12 so that we know where out of 12 we are. And we get 9.8, which is what month? Noor? Nope.
October?
Why October?
Well, I don't know, because if it's 9.8, it's probably closer to October than.
But you're either in one month or you're in the other month. Noor, what do you think? Okay, good.
Like when it says 9, that means the month is completed. So it would be like October then.
9 months have completed. Very good. So September's over. September is the 9th month, but it's over. And we're into October because we're into the next one after that. And once we hit 10, October will be over as well. I like to think of it like this as well. If it was 0.5, you'd be halfway through January. So the number's like one behind. If it's 1.5, you're halfway through February. You're not in January. You finished January, right? So you finish 9 months, you're into the 10th month. So this will occur in October of 1997. Okay? So there's a little trick there that you have to remember. Next one. Half-life of iodine 131 is 8.1 days. How long until only 15% remains? Half-life question. Do you remember doing these in grade 11 at least a little bit? Remember what a half-life means?
it's basically the amount of time that it takes for something to basically get to half its mass.
Yeah, that's right. So we're talking about radioactive substance, unstable substances that decay over time, and the way it turns out that it works is the amount of in a standard amount of time, like 8.1 days, half is gone. So if we start at 100, in 8.1 days you lose 50, but in the next 8.1 days you don't lose 50 again, it'd be all gone. You just lose half of what's left, which is 25, right? So every time you have less, but you're also losing less. And that's what makes it exponential, and that's what makes it decaying. It doesn't disappear into thin air. It turns into some other kind of substance that could also be radioactive, or it could be inert. And this is how they do things like carbon dating, which you've heard of, how they determine how old dinosaur bones are, that kind of thing. So what they do is when they find something old, like a dinosaur fossil in the soil, they would find some kind of carbon near it, and some of it will have decayed and some of it will not have decayed, and they measure both parts and they can see how long it's been in the ground there, right? So they use half-lives for dating things and for lots of other things as well. Okay, so the half-life is one of the ones where it gives us the multiplier. So I'm going to say m for mass equals m naught. We're using the b one here to the t over n. So m equals m naught equals b equals t equals and n equals. I'm going to skip m and m naught for now. What's b?
0.5 or 1/2.
Yep. What's t?
8.1.
No. T is what we're looking for. How long? T is time. So that's still what we're looking for. So what's n? N is the 8.1. Because a half-life happens every 8.1 days. Okay, so that's how that's worded when you have an n value. Yep.
I was just going to give M and M.
Oh, do you want to give us a... So m and m naught are a little bit trickier because it doesn't give them to us directly in the question. It says how long until only 15% remains. We don't know how much it started with. Turns out it doesn't matter. What's your idea?
For M naught, you put 1 for just like 100%, and then for M, you do 0.15.
Okay, good. So that's one of the sort of two ways that I would think about doing this. This is actually sort of the harder one. So if you don't like this, I'll show you an easier way that some people might prefer to think about it. Although this way will save us a step, when we move forward. So if 1 is 100%, then I'm left with 0.15, which is 15%. The other way you could have done it is think of your starting amount as 100, and then you'd be left with 15, like 100 milligrams, and you're left with 15 because that's 15%. Some people might find this way simpler to understand, thinking of 100 as 100%. But if you're fine with the decimals and the idea of 1, like I said, it will save you a step. Okay, so 15 equals 100. Make sure you don't get those backwards. 1/2 to the t over 8.1. Our first step is to divide both sides by 100. And 15 divided by 100 is 0.15. Well, look at that. Now I just have the step that we would have started at if we had used the other numbers. So see what I mean? It saves you a step. This is like a 1 here, and this is 0.15. You could use any numbers. You could pick 25 and figure out what 15% of 25 is. You could do whatever you want.
Is it okay if you don't use this method to solve them? Because I think,
How else would you do it?
well, just like log from the beginning and then like do the stuff that we were doing before where you like separate it and then,
Take the log of both sides when you have the 100 and make it log of 100.
yeah, kind of.
That would be a lot of extra work. But yes, if you did it that way and showed your steps properly and got the right answer, you'd get full marks. Try it once and see what you think.
I've already done it.
Oh, yeah, so that's fine. Okay, so now we're going to rearrange in logarithmic form. So this one, because there's an n value, has a little bit of a different extra step to it. T over 8.1 equals, base stays the same. So now I have to bring the 8.1 over to the other side. T equals 8.1 times log base 0.5 of 0.15. And if you're using the change base formula, it's 8.1 times log 0.15 over log of 0.5. and then into the calculator. $22.2 is what I got. Don't forget your therefore statements. This one's in days. No. Any questions? We're good? Yep.
How do we first write them into that logarithmic form?
How did we turn it into logarithmic form? So logs find exponents. Log base stays the same, 0.5, that was the half of 0.15 equals your exponent. If you prefer doing it this way because it's a bit more familiar in that order, just do it that way. Doesn't matter if t's on the left or the right. Does that work? Like it's the same as 2 to the 3 equal, or how about this? 8 equals 2 to the 3. So log base 2 of 8 equals 3. Remember, that was my suggestion earlier as a trick, that if you're ever kind of stuck and you're doing one of these and you're like, oh my gosh, I'm overthinking this, what is going on? Write that down on your scrap paper and make that goes there, that goes there, that goes there. Okay? Other questions? Okay, so those are the two examples of the exponential applications type. This one is the log scale type. There's only a few that we do, so if the question is talking about earthquakes or pH balance or decibel scale loudness, those ones are this type. They're all basically identical, the way that you solve them. They just work out the same. And so they're not super interesting, at least mathematically. What is interesting about them is, and we're going to explore this more tomorrow, so I'm not going to get into the specifics too much, but there are some things like the ones I just mentioned that are that we use a logarithmic scale for. And what does that mean? It means going from a 2 to a 4 is not a doubling. It's actually 100 times larger. So an earthquake that measured 2 and an earthquake that measured 4, the 4 would be 100 times more intense, not twice as like much energy in it. And that's why it's a logarithmic scale. And the reason why they do that is because otherwise we'd be like, we had an earthquake that was a 5. Oh, we had an earthquake that was 3 billion. And it would just be a scale that's really hard to understand how they compare. So for example, a 7 is fairly significant. An 8 or a 9 is like earth-shattering. Like there's, we've had 9s, I think, around the world in the past, but those are huge. And like a 5 or a 6 is really, really small. Like you barely feel it. 4, I don't even know that you would feel. So it's not like 4 to an 8 is just, oh, it's just twice as hard. No. It's like 10,000 times more intense kind of thing. Okay. So that's what logarithmic scales are. And like I said, we'll explore that a little bit more tomorrow. In 2010, the earthquake in Haiti measured 7.0 on the Richter scale. So that's sizable, but not huge. Do you remember this earthquake? You would have been quite young when this happened. It occurred to me that, every year you get further and further away from possibly remembering this. But some people have said they don't remember it happening, but they've talked about it in school and they've heard of it. Haiti was decimated by this earthquake, and they've still not fully recovered. It's a poor country, and just, I'm sure they've rebuilt a lot of the buildings, but I think they still haven't really got back to where they were, and this is 11 years ago now, right? So it was really devastating to that country. But in the same year, an earthquake in Chile measured 8.8, which is way bit larger. Why didn't we hear about the one in Chile? Well, because in Chile, they get big earthquakes all the time. They had I think the world record, which are the biggest that's ever been measured, which was like 9.5 or something like that, happened in Chile. And so they are ready for them kind of thing. So they weren't decimated by that earthquake. I'm sure there was some damage, but it wasn't like Haiti. So it's kind of interesting. Anyway, here's how we do these questions. We'll start with with Haiti. And so 7.0 is actually 10 to the 7.0. And Chile is 10 to the 8.8. Then we compare. And you always put the bigger one on top. Okay, bigger one has to go on top. Then we just solve. Get to the end, use our calculator. So 7 to 8.8 only sounds like a little bit of a change, but it's actually 63 times more intense. And that's how logarithmic scales work. If you're taking chemistry, you've probably learned a little bit about the pH scale and how it's logarithmic, but I know they don't teach you real much about what that actually means, so we'll talk about it a bit more again tomorrow.
So I just put it to my calculator like from the beginning and I still got it. So what is the minus 2? Oh,
Well, when you're dividing powers of the same base, you subtract the exponents.
I thought it was like 2 points and it says 7. So I just
Oh,
said
7. I know. I was writing too small there. 7 point. Oh, now it looks even more like a 2. 7.0. There, that's better. Okay. Therefore, Chile's earthquake was 63.1 times more intense. Okay, one more. And this one is sort of the other subtype of the log scales questions. An earthquake in northern Peru measured 7.7 on the Richter scale, while at the same time China had an earthquake that was about 7.9 times more intense. So it's not giving us the magnitude of China's, it's giving us the comparison. And we're solving backwards. This is the other sort of type. Determine the measure or the magnitude of the earthquake in China on the Richter scale. So for this one, we need a let statement because we're introducing a variable. And if you just all of a sudden start writing x and nobody knows what x means, that's not appropriate, right? So let x represent the magnitude of the earthquake in China. And so China becomes 10 to the x, and Peru is 10 to the 7.7. Which one's bigger? China's was bigger, so it's going on top. 10 to the x over 10 to the 7.7 equals... 7.9, right? The other number that we're given. Ten to the x minus 7.7 equals 7.9. Rearrange into yep. Go ahead. X minus 7.7 equals, no, there's a bit more to it. It's not just equal to the exponent.
Log 7.9?
Yeah, log, and base 10, right, which we don't have to write, but I'm going to include it just because otherwise people might be confused. So log base 10. Move the 7.7 over. I'm going to put it out front for clarity to make sure we know what the argument is and it's just clear. I think some people earlier were not putting it out front, and I think they did this. Just watch. Log 7.9 plus 7.7, and obviously that's wrong because now the 7.7 is inside the argument of the log. So put it out front and you'll be safe. Therefore, the earthquake in China measured a 8.6. So that one's a little bit trickier when you have to solve for x. You got to remember to do a let statement. But you see what I mean? Those ones are always kind of going to be the same. 10 to the this over 10 to the that. That's it. Any questions? Last thing I just want to show you is when you go to do the practice, take a look at how they're all jumbled together. So, it sounds easy at first, but I think once you get into it, it's not necessarily as easy as it sounds, that you got to identify the type. Bacteria culture doubles. Okay, doubling, we see that word that's there, so that's an indicator of how we're going to do this one. Number 2 is a half-life question. There's a couple in here that give you an equation that you just have to use. Okay. There's one about an investment, one about population. There's another one about earthquake, and one about a pH scale. So there's a real mixture of different kinds of questions in these.